Okay. So welcome everybody to today's imaging seminar. We're very pleased today to host Antoine Laurain from Sao Paulo. And let me say a few words about Antoine as ways of introduction. He obtained his PhD from Universidade de Laurain at Nancy in 2006, where he worked on singularly perturbed domains in shape optimization, and his advisor was Jan Sokolowski. Antoine then spent time at several places, at Graz, at the University of Aachen in Berlin, until he joined the Institute of Mathematics and Statistics of the University of Sao Paulo in Brazil, where now he's associate professor. Antoine's research interests include PD constrained optimization problems, shape optimization, inverse and free boundary problems, and with in particular applications to image analysis, among other things. And his talk today is titled Shape Optimization Approach for Sharp Interface Reconstruction in Inverse Problems. And let me just remind you that, as usual, we'll take questions during the talk. If you want to ask questions, please use the chat or raise hands, and we'll unmute you so that you can ask your questions. Antoine, the floor is yours. Thank you again for accepting our invitation.
So thank you very much for the kind presentation and the invitation. I'm really happy to participate in this SIAM imaging seminar. And so the talk is 45 minutes, right? Just to...
Yes, about.
Okay. Okay, so this, I'd like to talk about several results, and these are parts of a project which is called STMI project in the Research Center for Gas Innovation, which is located at the Poly-USP, the Polytechnic School, so it's the engineering school of the University of Sao Paulo. I'm at the Mathematics Institute, but we are part of this project. And so these are works with several colleagues, two colleagues here from the project. Yuri is my student, Keith, he was a postdoc, now he left, he's working somewhere else. And also with Kevin Sturm from Austria and Irwin Youssef from Germany. So I'd like to talk mainly about two types of inverse problems. The first is electrical impedance tomography. And then in the second half, I'm going to talk about the similar application of shape optimization for another inverse problem of full waveform inversion. So electrical impedance tomography, as I think many people know in this seminar, I guess, is a famous ill-posed inverse problems. And so just to summarize the ideas of the model that we consider here, we consider a domain D, which is the square here. And we are applying electric currents on the boundary of D, and we measure some voltages H also on the boundary. And the goal is to reconstruct the conductivity sigma, which is matching the measurements H. So the particularity of our approach is that we consider discontinuous functions sigma. So here, in general, we consider discontinuous function, but here I'm going to focus on piecewise constant functions. So this sigma is equal to a constant sigma 1 here in some domain omega, which may have several components. And so sigma is equal to sigma 1 in these three inclusions, and in the background, it's equal to another constant sigma 0 in this omega complementary. And this is the ground truth. So this is the real conductivity that we want to reconstruct. And this is an example of reconstruction that we obtain. And I'm going to explain how we do this later. So just a few words about applications. So EIT is an interesting problem for application because it's a low-cost, non-invasive, radiation-free, and portable imaging modality. So these are the advantages, but it also has a few drawbacks, such as the poor signal-to-noise ratio and poor spatial resolution. So there's a lot of references discussing these issues and these advantages. but it's already find its way in applications. So for instance, so you have three interesting families of application for medical imaging. So here I'm showing several possibilities. And here at the University of São Paulo, there's a very nice group of Professor Lima, who is using EIT for monitoring patients undergoing mechanical ventilation. There are also applications in geophysics. Often this is then called electrical resistivity tomography, but it's very similar to EIT. And so there are applications for mineral prospecting, map groundwater, etc. And you also have application in civil engineering, mainly for crack and void detection in general, and non-destructive testing. Okay. So now I'm going to describe the mathematical model. So the simplest mathematical model is the continuum model, which is very interesting for the, let's say, for the pure mathematical point of view, because it gives a very challenging problem, which has been studied by very renowned mathematicians since it was introduced by famously by Calderon. So here in this model, the currents and the measurements, they are supposed to be known on all of the boundary. And then more recently, people have started looking at the continuum model, but with partial measurements. So the idea is to consider only currents and measurements on an accessible subset of the boundary. And then there's a more realistic model, which is called electrode model, where the currents are sent along wires, which are attached to n electrodes along the boundary. So in these photos, like here you can see an example of this more realistic setup where you have the electrodes attached to the boundary here of the body. And here I'm going to talk about a kind of simplification of this electrode model, which is called the point electrode model. So the idea is to replace small electrodes by point electrodes, which are modeled by delta distribution. And this model was studied more recently in these papers from Yvonen, Anke, Chenel, and others. So the idea is to simplify with the electrode model, because in some situation it's interesting to use this delta distribution, especially in geophysics, as I will show later, where the measurements really located on points compared to the large scale of the physical problem. So as I said in the beginning, we studied a particular case of sharp interface models, which was studied by a few authors in the literature. So here, mathematically, the conductivity is piecewise. So we use an indicator function chi. Chi of omega is equal to 1 in the domain omega. And so that means sigma is equal to sigma 1 here in this omega, which may have several components, and equal to sigma 0 in the background. So essentially, the unknown of the problem is to reconstruct the interface of omega, okay? So that means these two interfaces here. And the currents and the measurements, they are performed on a subset of the boundary gamma. So here we reserve some small portion of the domain for a grounded region, for instance, where you have Dirichlet conditions, or you can have gamma 0 empty, for instance. And then the mathematical model, which is considered usually for EIT, is that U is the solution of an elliptic boundary value problem. Here we consider a mixed boundary value problem. We have considered a slightly more general problem where we have a source F, which usually in EIT this F is equal to 0, but here we have, for the calculation, for the theory, we have considered a slightly more general problem. But usually the applied currents, they are here in this function G on the boundary. So here the solution U is in H1, the gamma is just to represent the fact that we want U equal to 0 on this gamma 0. The F also can be piecewise constant or piecewise smooth. And we have some partial measurements also on a subset gamma H of the boundary. Also, for the optimization approach that we use, we consider a set of currents and the associated measurements HI, on the boundary gamma h, which are associated with the ground truth conductivity sigma star. And ui is the potential which corresponds to gi and to the trial conductivity sigma of omega. So you have the trial conductivity sigma of omega, which is different from the sigma star during the optimization. And so now the EIT problem is reformulated as a shape optimization problem where given the data of the GI and the HI, you want to find the shape omega such that the UI approximates your data HI, okay? As best as possible, because usually you have noise in the data, so you cannot have, you can't have really the equality here. And the particularity here is that we studied the case where gamma h is a set of points instead of a continuous region. So the optimization that we consider is to minimize the j of omega, where you have ui of xk minus hi of xk. So you have the sum over the points, and you have the sum over the currents. Okay, so if you have if you don't have point, but you have a thick region where you can do the measurements, then you would have an integral here instead of the sum over the points. Okay, but I think you already observed that there's an issue with this ui of xk, because if ui is only in H1, in general, the ui of xk is not well defined. Of course, you could use some additional regularity for these elliptic problems, but for the optimization, this is problematic because when you define the adjoint, you're going to lose some regularity. So somehow, to do the optimization rigorously, one needs to define a different setting for the function spaces. So there are several possibilities to do this, but what we did is to use an approach which is known in optimal control. So the idea is to use, instead of using the H1 space, we use the W1P space. So this gamma is also because we want the trace on gamma 0 equal to 0. And the idea is that this W1P is a little bit more regular than the H1 space because we have the P equal to 2. So you have to think that this P is just like a 2 plus epsilon with a small epsilon, okay? So we just reduce a little bit the space to have more regular functions. And this does the trick because now we can define U as the solution to the mixed, this mixed boundary value problem. So it's similar to the other formulation, except that now the test function, they are in the space W1P prime. And the P prime is the conjugate of P, so it's smaller than 2 now because the P is larger than 2. So the P is like a 2 plus epsilon, and the P prime is a 2 minus epsilon, okay? And our main contribution was to extend, to use this theory, which was developed by Kröger in this paper for W1P estimates for mixed boundary value problem. And we have extended a method which is called average adjoint method to Banach spaces to accommodate for this formulation, okay? So this allows us to compute the derivative of this shape functional, this one, because it depends on the shape omega. And this functional involves point evaluation. So this is in fact a general